Okay, so hello there. I am Arafat. I am an undergrad at the Indian Institute of Technology, Kharagpur, and I just recently came here from India. And today I'm going to be talking about TensorFlow.rb, the Ruby API for TensorFlow. And before I start this talk, I just want to stop for a second and tell you guys that I've only been to Hungary for like a very short time, but I feel like you guys are like really welcoming and really sweet. So thank you so much for being like this. So coming back, I've always loved solving interesting problems. One of which is this. And I started this project in the summer of 2016 with the funding from Somatic.io. And after that, I was awarded the prestigious Ruby grant from the Ruby Association. So in the summer of 2017, I was working at Medical Image Analysis Lab, Simon Fraser University, Canada. And in the field of in the field of medical imaging, we're solving many fundamental problems using TensorFlow. And even the medical imaging community is like really interested in solving machine learning problems in areas like retinal imaging and diseases like diabetic retinopathy. So for me, it's really nice to be able to look at the real world examples of things. So coming back, the question is, what is TensorFlow? So show of hands, how many people here use TensorFlow in their work or in their projects or anything? So like, just for fun projects, just for hobby, even if you solve the tutorial, just show your hands up, it's okay. Okay, that's great. Okay, well, I was expecting like there were more people, but never mind. It's okay, it's okay. So coming back, TensorFlow is the world's largest machine learning library for numerical computation using data flow graphs. Nodes in this graph, nodes like softmax linears, etc., they represent mathematical operations, while the graph edges represent tensors. Tensors are basically multidimensional arrays that are communicated between them. So TensorFlow project was open sourced 21 months ago by Google, and today it has gotten so popular that it has 71,000 stars on GitHub. So that puts it #1 in the machine learning category on GitHub. And as someone who watched it grow right from zero, I have found this to be an amazing journey. So TensorFlow was originally developed by researchers and engineers at the Google Brain team with Google's Machine Intelligence Research Organization for the purpose of neural networks and deep neural networks research. So originally, it was not meant to be something that was to be open source and to be used by everyone. It was just basically for researchers. But now they realize that, OK, a lot of people are going to use it for a lot of things. So it's probably a better idea to open source it. So in 2015, they open sourced it. So before I start dwelling on TensorFlow, just show of hands, I just want to ask how many people here are students, like college-going students, and are just like new with open source and machine learning? Like, is there anybody here who's like really new? It's okay. Like, it's not a crime to be a newbie, right? Everybody starts at some point. Okay, so that's great. So I just want to like emphasize that I've come from a university which has like a very strong open source culture, and we are at I'm from the Indian Institute of Technology, where we are at third in the number of most selected students for Google Summer of Code program, and like we have got a strong culture for GSOC, for Railgirls Summer of Code, and for Outreachy and other programs. So if you want to talk about like open source grants or about student programs, just come up to me and talk to me. It's totally okay. The thing about, OK, so now that I've done that, so the thing about TensorFlow is that it's not something that's just for like very experienced developers or researchers. It's literally for everyone. So even if you're like a student and if you're a noob in Python, you can just go through a tutorial in TensorFlow. And you may not understand like everything, but it's still perfectly OK to go through it. And it's obviously it's open source, flexible and production ready, and scales easily from research to production. So let's go through a small timeline for TensorFlow development. So initially, it was released to public on November 2015. And after the initial release, they also released many things like Python version 3 for Python version 3.3. They also released TensorFlow serving, which is a flexible, high-performance serving system for machine learning models. And they also released it on mobile platforms and did other things like GPU acceleration. So another cool thing I wanted to elaborate is that TensorFlow version 1.0 was released in February of this year, and they had this huge conference for TensorFlow Dev Summit. So there are a lot of amazing videos from the core developers of Google Brain Team, and you can check them out. They're totally amazing, even if you don't understand machine learning. So TensorFlow developers felt that it's really important for TensorFlow to work on various platforms. So mobile platforms are very important, and also aside from that, it runs on CPU, GPU, and custom accelerators like TPU. So TPU is like Tensor Processing Unit, and Google and many other large startups from across the world are using it. Aside from them, mobile platforms like Android, iOS, and Raspberry Pi are working. And for language bindings, we have Golang, Python, C++, Java, and more, and Ruby, obviously. And so in February 2017, TensorFlow 1.0 was released, and along with that, they released TensorFlow C API. So all the language bindings for TensorFlow, they basically work fundamentally in the same manner. And the idea is that all of them connect with the TensorFlow C API to be able to make function calls to the C API. And so after the release of the C API, a lot of developers from across the world felt that that they could build language bindings, and there was a very heavy discussion among people. And so Google themselves and a lot of external developers like me came along and started working on this project. So here's the issues page for the Golang API. As you can see here, there's a proposition for how an idea for the basic version of the Golang API would work on. And as you can see, like, it's got a lot of comments, lots of people talking about it, and it was like, I'm very thankful to these guys, because the thing about Golang API is that even though the language is very different from Ruby, a lot of the ideas that they had were actually pretty helpful for Ruby, and for all the other language bindings, this was where it all started. And this is a discussion page for the Java API, again, very popular, and this is for the Ruby API. So as you can see, like, lots of comments, lots of people showing their love, literally love. There's like a love mark with 26, so I don't know. And this issue was finally closed on 16 June 2017. That was when the TensorFlow team accepted my version as the official TensorFlow Ruby bindings. And if you go to the TensorFlow API docs, you'll find the links for all the language bindings, and including the Python, C, C++. And if you click on Ruby, you will be directed to our version. So before I talk about like the API of TensorFlow, and before like I dwell upon example stuff, I want to show you like a few dependencies of TensorFlow. And the reason I want to do that is because a lot of developers are here, and you work on many interesting problems. So it's not necessarily a machine learning thing. And if you use these dependencies for your own work, it's probably going to be a lot helpful, and it's better than the existing options that you're using. So the first thing I'm going to talk about is Swig. So Swig is a simple software development tool that connects programs written in C and C++ with other high-level programming languages like JavaScript, PHP, Ruby, and so on. So what Swig does is that, as you can see in the code, it expects you to have ANSI C++ declarations, basically like functions, C functions, C variables, and so on. It also expects you to give Swig type maps. So these are like this string vector, integer vector that you see here. This is a Swig type map. So the standard Swig library contains a number of modules that provide type maps for standard C++ library classes such as std pair, string, and so on. So what you can do is you can basically access the STL containers, the standard temporary library containers of C++ from other languages easily. And let's just say, look at this example. So it's basically, there's the C++ code, and it's a function that calls for sum, and it expects the parameter as a vector of floats. So it seems pretty easy in C, C++, but when you use it in other languages, how do you make a call to this function? So with Swig, you can just, instead of writing a type map for vector or floats, you can just directly use the module std_vector.i. So with that, you can use a vector inside Ruby, and then making the function call will be excellent, and it would be pretty easy. So when we were using the TensorFlow C API, what we found is that there are a lot of gems that help you make language bindings, but none of them actually had a feature that was this easy to use. So that's why we didn't use Ruby FFI or inline or other options that we had and work with Swig. Other thing that we'll be talking about is Google protocol buffers. So protocol buffers are kind of like XML, but to give you a simple definition, protocol buffers are language neutral, platform neutral, extensible mechanism for serializing structured data. So the method involves an interface description language that describes some data and a program that generates source code from that description and presents the structured data. So what you do is you define data structures in text files, and protobuf tools generate classes in Ruby and C and Python and other languages corresponding to those text files. And using that code in the other languages, you can load, access, and save the data. So let's just see. So this is a simple example of a message written in protocol buffers. Pretty easy to understand. It's almost like written English language. So there's just a name-value pair. So let's just say required string name1. So the name would be name, and the value would be 1. So the value of the value in the name-value pair could be a bool, integer, string, or even another protocol buffer message. So you write these down in protocol buffers, and then you can serialize them and parse them to raw bytes, and then using the protobuf compiler in your chosen language, you can generate a class for this, and that class will be able to access this data and edit this data. So why not just use XML, as I talked before? So the answer is pretty simple. It's the code is really easy to understand, and if you saw it right now, it's basically like you're writing English language, and it's less ambiguous, easy to understand. And when you actually look at the size of the bytecode, I've actually seen that it's a lot smaller than XML. So you're being efficient memory-wise, and you're actually also being faster than XML. So now I can actually introduce you to some TensorFlow.rb classes. So a few classes are tensors, opspec, ops, graph, and session. Now I know these words seem totally outlandish to you because they're like, oh my god, what is this? But all these things are pretty easy. Just let me walk you through this. Okay. So tensors. So tensors are basically like the Bible for mechanical engineers. If there's any mechanical engineers in this talk, they will be like, oh my god, tensors. Okay. So it's well, it's not what you think if you're a mechanical engineer. I have a different idea for tensors, so I'm disappointing you again. Okay. So tensors are a mathematical object analogous to a vector, and it's represented by an array of components that are functions of coordinates of a space. But in our case, basically what we do is that we use an n-dimensional matrix as a tensor. So you think of matrix as row by column, but think of n-dimensional matrix as row by column by height by another dimension by other dimension, and so on and on. And this is, by the way, this is a stress tensor, just in case you're wondering. Okay, so this is a simple example usage of the class. Now, the parentheses are so complicated, you might not be able to tell, but I'm telling you that this is a matrix with the dimensions 2 cross 3 cross 3. And it has rank 3, and it has type integer. So using the Ruby API, there's a lot of fun stuff that's happening internally when you define this tensor class. But there are a lot of calls to C, but it works seamlessly for you. And if you make an error in this, you'll get a warning message, and everything is good. Other than that, there is the operation. So operation is so I said that TensorFlow is basically data flow graphs. So graphs have nodes. What are the nodes in TensorFlow? operations are the nodes in TensorFlow. So operations take input as 0 or more tensors, and operation could be something really simple like addition, multiplication. And if you think about it, like every single machine learning task, everything can actually be represented like as a graph, and the nodes of that graph would be some operations that you're doing. I'm going to literally show you that so that you believe me. So I'm going to talk about OpSpec class. So OpSpec is basically the class for specification of operations. So look at the code. It's pretty simple. Basically, you're defining an operation. The operation has name determinant of matrix, and it has type matrix determinant. It has no attributes because attributes are there for like very complicated operations, but this one has no attributes. So simple matrix determination thing. And it expects an input in the form of a placeholder. So now I'm going to talk about what is a placeholder. So here we go. So placeholder is basically like saying, hey, I'm going to mark this place, and I'm going to put some data here later on. So placeholder, basically, think of it kind of like a bookmark for data. And once you have a placeholder, you're basically going to give data at the placeholder later on. So I'll explain in greater detail. And then there is session. Session is a class for running TensorFlow operations. And session encapsulates the object environment for graph. So like the whole graph is ran actually by the session. Graph is in itself is just like, it's like you write the whole code, but then you compile it with a compiler. So think of session kind of like that. Not exactly a great analogy, but had to do with this. So okay, so finally a simple example that you can actually understand. So this one's pretty simple. So first what we did was we defined graph.new. So what we did is we defined an empty graph. It is an empty graph object. Then we have tensor1 equals tensor.new and then matrix. So basically we have tensor1 and tensor2 as two tensors that we have defined. Now we have placeholders. So placeholder 1 is corresponding to tensor 1, and placeholder 2 is corresponding to tensor 2. And we're using the method graph.placeholder. So basically what we're doing is that we're marking inside the graph that, hey, at this point, I'm going to give you a tensor, and I'm marking it with the placeholder. Now after that, we have OpSpec. OpSpec is the operation specification. It's the operation that you're going to be applying on your graph and on the tensors. So this, what you're doing here is that you're adding two tensors. So the operation name is addition of tensors. It has type add, and it has no attributes, and it expects placeholder 1 and placeholder 2 as the inputs. Now finally we have session. So session.new method we're using to make a session corresponding to that graph. So that's why graph object is the input. And finally, we have a hash function. So what this hash function does is that it makes a mapping between the placeholder and the corresponding tensor. So you see that hash placeholder 1 equals tensor 1 hash, placeholder 2 equals tensor 2. It's making a mapping between the placeholders and the corresponding tensors. Now we finally give this hash as an input to the session, and we run it. So basically, what did we do here? At tensor 1, we defined a matrix. A matrix was 2, 2.3, so on. And tensor 2, we defined another matrix, and then we added those matrices, and we got a result of adding those matrices down here, which is like, I commented the result, which is 6, 5.5, so on. So like, nobody has ever complicated matrix addition this much. Like, nobody, but it's okay, I'm doing it. So, well, this was a really simple example of matrix addition, and this looks like really complicated. But think of other matrix operations like inversion or determinants, or like finding diagonals, solving a system of linear equations, and decomposition, and so on. So if you must know, like we have, I'm sure people here might have used NumPy and other Python scientific libraries for matrix purposes, because they're like pretty standard. So if you must know, there's corresponding to that, we have an n-matrix gem in Ruby, and it's a watered down version of NumPy. No insult to the developers, but it's true. Okay, so by using TensorFlow, you can easily replace all the matrix operations of that here. And now there's an explanation for protocol buffers. I was talking about protocol buffers. Well, there you go. So for the simple graph that I had here, this simple example where I had two placeholders, I have this as, so what you do is that you save the graph in the protocol buffer format by a simple line. You just write the graph to a file, and then you try to read the file to understand like what is the actual information in the protocol buffers. So as you can see here on the left side, we have a node 1, and node 1 has like tensor1. It has op of type placeholder, and it has a few attributes. Most of the attributes are empty, but there's an attribute for data type, which is the double data type. You can specify like the data types and everything for tensor construction. It's pretty easy. And similarly, you have tensor2 corresponding to a placeholder. So tensor2 is also almost exactly like tensor1, and you're seeing their graph definitions. And it's now after that, we did an operation of addition of two tensors. So this is another node, and this node has op name add, and it expects two inputs, tensor1 and tensor2, and it has the attribute double. So think of it like this way. Like, let's just say you have a graph, and graph has a parent node here. Like, this parent node is for addition, and it has two children nodes here and here. So these children nodes are tensor1 and tensor2. So this is a graphical explanation of what we did, and I'll actually show you the graph so that looks better. So now I'm going to talk about the real gains of protocol buffers. So what we did here was something incredibly simple, like addition of matrix operation or something like that. But imagine doing that, like doing this simple example here, and then doing it again in like Raspberry Pi or Android. All of these platforms are totally different from each other. And the protocol buffer explanation that we have here will be identical here. So what you can do is you can define a model here, and you run the same model in Raspberry Pi and across all different platforms, and it's going to work exactly the same. So this is the amazing power of TensorFlow, is the compatibility and the ease of like transferring stuff between different languages. So basically what we have done is like we have models defined in Python, and then we use those models everywhere else. And the same thing can be done in the reverse way too. You can define in Ruby, use it in Python, and so on. And second thing is easy to understand. And finally, also to debug. So if your models are small enough to be debugged, you can read the protocol buffer explanations and debug if you have something wrong, or use other options too. Now, there is a problem here that what's stopping us in our developer? Like, I literally met somebody before like the conference, and they were like saying, we're using the Python API. And I was like, OK, cool. But what's stopping the language bindings from not exploding as much as the Python API? I mean, they're also good, right? So the problem is the underdeveloped C API. And that's something that's totally up to Google. I mean, I can't like push that stuff. So to give you an explanation of the underdeveloped C API, and the reason I'm talking about C API is because I have said it before, maybe you might not have remembered it, but all the TensorFlow language bindings work in a way that they'll first connect to the C API, and make calls to the C API. Everything that you do accomplished by TensorFlow language bindings is only because of the C API. So all of them have equal capabilities, and all of them are equally limited. And that's like a common factor among them. So let's look at this comparison chart. So in Python, you can do something like run a predefined graph or do a graph construction. The same thing can also be done in the C API, so you can also do that in Ruby. But you can't do things like gradients or other control flow or neural network library options. Now, when I said that you can do this, it doesn't mean that you can like totally not do this. You can define a model in Python, transfer it to Ruby, then you can run it. By default, constructions is not possible. So let's have some fun. Like, we have had like a lot of very nitty-gritty details, and it's like maybe it's time to do a little fun things and so on. So one of the classical problems in machine learning is image recognition. And in the last few years of machine learning, researchers have made tremendous progress on addressing these difficult problems. And a kind of model called convolutional neural networks is pretty good to solve image recognition problems. And one of the standard data sets for image recognition problems is ImageNet, and there's a competition every year to improve the results on ImageNet. So obviously, like Google would participate too, and in 2012, they open sourced all their code for ImageNet competition, and that was a model called Inception v3. So all the models for from Google for image recognition is available. And this is a very abstract concept, but this is like a graph of how you could a very rough explanation of how you use Inception v3 model, and it's a very complicated model. To give you an example, like we defined a simple protocol buffers graph before in this talk, and that was like a few bytes. This model, that model would be 56 megabytes. So you can imagine like it has millions of add multiply operations and so on, and it's pretty complicated. And it's like the research paper has been open source, and people are still trying to figure out how this works. Even the people who wrote it are still trying to figure out how this works. So on a modern processor, on a modern PC without a GPU, this model works in a fraction of a second. And now what we want to do is we want to be able to run this model for ourselves. So if you download it and if you use an example from the Tensorflow RB website, the way it works is pretty simple. You load the serialized representation of the pre-trained model into a graph. And you get this serialized representation or the graph model downloaded from Google. Then you load it into a graph. Then you create a session to execute the operations on the graph. And then you convert the image file that you're using as a reference to run on that will be provided as an input to the session. And then you execute the session and print the label of the image file. So maybe this sounds like a pretty abstract thing right now, but I'll just literally do it for you. And you can also replicate this by following the tensorflow.rb page. So this is a really cute puppy, and okay, something we can agree on. Okay. Okay, so we want to be able to figure out what this puppy is and what this is like, because to a computer this is just a string of zeros and ones. So when we ran the model on this puppy, the results were it's showing with 85% accuracy that this is a golden retriever. So that is like a pretty amazing result, and it may have something to do with the image being like really up close. Like the image is like really up close, so maybe that's why it has a very high accuracy. And then there's lower accuracy for things that have lower chance of being that. Now, I kind of like the puppy a lot, so maybe take a look at it again, just So last night, me and a few other speakers were roaming around the beautiful city, and it was like really fun. And I had this idea that maybe we should do something meta and something. So I thought that so this is like a Sechenya Bridge. I hope I'm pronouncing it right. I don't know. So this is a picture of Sechenya Bridge. I did not take this picture, but it looks pretty amazing. And we want to be able to run our model on this image. So let's look at the results. So it says with a 62% accuracy that this is a suspension bridge, which seems pretty good. And this is like the whole deal of Inception v3 model. There are around 1,000 classes, and if you give it the images of any of those classes, it works like really well. And I recommend that when you go back, you can just go through the TensorFlow RB page, try out this example for yourself, and actually take pictures from your mobile phone and try this on those pictures, and you'll be surprised by the results. Another cool thing that I'm going to be talking about is TensorBoard. So the thing about machine learning models is that when you look at the code, it's there, but you just want to know more. And For that, to be able to understand even the code written by yourself better, you need a visualization tool. So TensorBoard is a tool for understanding your data flow graphs better, for visualization and plotting quantitative metrics. So quantitative metrics would be something like, let's just say you have a model, and it goes through many different iterations of training. During different iterations of training, the accuracy improves. So you want to be able to plot it quantitatively and compare different models, like which model is improving a lot more than the other models. So for that, we have quantitative metrics. So let's take a look. So this is a data flow graph of the first one, the first example that we have, which was the addition of two tensors. For that, we have a graph, and this is like pretty simple. The two tensors are tensor 1 and tensor 2, and the parent node of these graph is the addition node, which adds these two tensors. Now, this is another cool photo. It is plotting of the quantitative metrics between different models. And as you see, if you look at the bottom, you see that some of the models really improve with the different iterations, but others would not improve so much. So that will help you figure out which one's better for you. Now, this one's like really cool, but I don't think like people could visualize this inside their heads, but I'll just give it a try. So this is a picture from the MNIST dataset. So basically, MNIST dataset is like you have a lot of handwritten digits like 1, 2, 3, literally written by hands. And what you want to be able to do is that you want to take these pictures of numbers written by hand and be able to classify them. And this is a very classic and simple problem. And in lots of tutorials, you will find this problem. So what we have here is that this is a 2D shot of a 3D image. So let's just say like we have different clusters here. Every single cluster here represents a group of numbers. So suppose you have like a 1 written, so it will be in a cluster of 1s. If you have a number like 9 written, so 9 will be among a cluster of 9s. And every once in a while, if you look closer, you will see that there are a few red marks here. So at the bottom, there's like, for 4, there's a red mark. So what these red marks are is like, it's an improper classification. Like you would not find a 4 among a cluster of 6. And that is a problem here. So for that, we have actually marked it red and showed that, OK, our model failed on this one. But OK, so maybe just take an actual look at this. And I don't understand. So this is the 3D explanation. Like I'm actually moving the 3D space myself. OK, let's see. So like you can see, like there are different clusters. Like there's 2, 3, and so on, different numbers at different places in the 3D space. And you can look at these, visualize these for yourself, and help you understand how classification works. So this is a very classic example of a classification problem and how you could visualize it and extend it to other domains as well. So wrapping our talk on TensorBoard, so a simple example on TensorBoard would be available on TensorFlow RB webpage. And also on the TensorFlow website, there is an amazing tutorial. And at the TensorFlow Dev Summit here, there was a complete talk on TensorBoard. So just a 10-minute talk just on TensorBoard is also available. And if you Google on YouTube, that's the first result that you will get. And so I also want to mention that I received like a lot of so now that I'm done with TensorBoard, I want to mention, like, wrap up this talk, and just want to mention that I received a lot of love from the Ruby community for doing this project. So on GitHub, we were trending for quite a few weeks, and also on Reddit. So I don't know if you guys here like use Reddit or not, but social media in social media, Reddit has been something that's been really helpful. And I got a lot of my followers from Reddit, and we were trending there for weeks too. So if you don't use Reddit, I recommend that. It's something that's incredibly helpful as a programmer. And if you're into Ruby, it's great. But even if you're not, like, there's dedicated subreddits for all different languages and even for general programming experience. So lastly, I want to say that I'm very thankful to all of you guys for this project. So I started this project in the summer of 2016 with the help and support from Somatic.io. And my mentors were Jason Toy from Somatic.io and Dr. Soon Hin Kaur from IBM Research Tokyo. and currently he's the CEO of Ring Capture. And I kind of emphasize on how much these people help me. Like I would always, like sometimes I would get stuck somewhere and these people would give me valuable recommendations like, hey, you could do this, you could do that. And I think that's one of the most helpful things about the open source community. So even in the people who are present in this room, we'll find that some of these people are like incredibly talented at the top of the developer game, and some of us like might not be in the newer stages, and we can always reach out to these people and be like, hey, I need help with this. And that's the thing that's very helpful, that we should not be, if you're a new developer in open source, you should always like go talk to somebody who's like much better than you. And more often than not, you will find that they'll be very welcoming and helpful. And it's just like your way of approaching that matters here. And I wouldn't say the same for academia or for other places because I've been there, so I know. So. And lastly, I'm thankful to Mats and the entire Ruby community and Yuriku. So thank you so much, everyone.